Well, yes. Um, Today I'm going to talk about my students with the ICE synthesis for the ICE 40. I've been working on that for a bit, and I'll run folks in the background there. Um,
Your
I,
audio, your audio is kind of iffy, Brad. It sounds like you're using a speech distorter disguiser. Now it's going away, so we can't hear you. Or maybe it's me.
my head was I was trying to move the video to the side and then wasn't facing the right direction. Um, so I'm going to talk about FPGA synthesis for the X40. Something I've been working on doing in Forth for a little while now. And I ended up somewhat undergirding approach, and I'll talk about why and how this relates to a thing called the flyweight pattern. And it's the thing that I've discovered along the way that I'm calling Superfly for now. And then I'll talk about more about the status of the project overall. Let me go to the next slide.
You're
Background for
still
anyone who's not been following along, I've now, quite a while ago in 2003, I was gifted a device board, which is a
wow.
um, yeah,
Yeah, we're having problems with your sound quality, Brad.
let me apply.
Oh, is this better?
Much better.
Much better. All right, let's go with that. Okay. So so back in 2023, I was gifted a Pico Ice by Christopher Lazinski. And this kicked me off on an interesting adventure. This particular device has a Raspberry Pi Pico on it. Or sorry, it has a Raspberry Pi Pico, which is an ARM-based CPU with 264K of RAM. But it also has an ICE 40 UP5K, which is an FPGA that has a sizable number of LUTs and a bunch of flash memory and things like that. It has a LED and whatnot on the device. And it proved to be pretty easy to port micro eForth, the same engine that's used for ESP32 Forth, to run on the device. Um, and but of course, sitting behind that is the more interesting challenge, which is that this particular board is configured in such a way that the FPGA can be all of the pins of both the FPGA and the CPU are exposed, but the FPGA can be controlled from the CPU, so you can stream over new images over SPI to the FPGA. And so it occurred to me that it would be cool to do something with that FPGA. The FPGA has 52,000 something LUTs. It has a bunch of RAM on it, has some additional dual ported RAM, and it has some digital signal processors. And it's part of a larger family that has sort of the same structure. And the cool thing about it is that unlike a lot of FPGAs out there, an open source community of folks has managed to reverse engineer the bitstream format. So it is one of the few architectures that has sort of a well understood bitstream format, and they've even built an open source Verilog for it, called Ice Storm or Ice Pack, and a bunch of information is out there, including things like a visualizer for the output of the format. And so it's cool to be able to use open source tools, but what I'm particularly interested in is the idea of being able to use Forth to synthesize for it and to do this interactively eventually is the goal, so that you'd be able to describe the gates that you want to lay down, and then have those, kind of spring to life on the device, do something with them, and then maybe reconfigure the device interactively. Um, of course, in the intervening time, one of the biggest challenges is that the format is by no means simple, and I've struggled to unravel it, and I'm pretty close there. I've got a bunch of it pretty well understood, and one of I think the challenges is sort of there's a stylistic difference of approach. The open source tools that are out there are built around a database of information about the various routes through the device. They're carefully, labeled in certain ways that are somewhat uniform, but really their focus is on ultimately being able to throw all of this at a tool that runs on a desktop computer and can chew over these things as in a generic way. And this obscures the very regular structure of the device. Each of the different cells in the device are basically identical. There's some little differences in terms of a few strips of special ones in the array of cells, but by and large, they're kind of the same element repeated over and over again. And so this is kind of what it looks like for the 5K version of the chip. These purple cells in this particular visualization, the bright purple or bright magenta ones are just ones that actually have config in them. But the purple ones are generic logic cells, and then these yellow ones in these two bands are RAM cells. And then the black and the cyan ones are I/O pins. And then sitting kind of outside of this is some of the other stuff. There's some things not labeled in this diagram up in this part of the thing. There's a little bit of global config bits that are sort of just scrolled in a particular place. And but anyways, like the logic cells have 8 LUTs in them, and they're arranged in a configuration where they're by LUT I mean a lookup table. So a lookup table going from four input bits to a single output bit. There's some additional configuration that routes in a carry for each of the cells, and then these lookup tables are fed into a D flip-flop. And then there's some options to where you get the clocks from and so on. And the configuration RAM is basically stored as a big bitmap. It is split up into 4 banks that are kind of mirror reflections of each other. To give you some idea, this one is not actually for the 5K, but I grabbed this image from one of the documents. The 5K, it happens that there are these 4 banks, but they're asymmetric, where the bottom two are slightly smaller. But anyways, the way you can think of it is that you've got configuration that's really just a bitmapped image of this size, and sort of here's a different visualization for the ICE 5K. Actually, that is showing some output from my synthesizer. And each of these, by sort of putting the right bit patterns into each of these cells, you're able to lay out logic in them, and we'll talk about that in a second. Um, the biggest challenge with all of this isn't actually the gates. That part actually has a pretty regular config, and there's a particular 16 bits that determines the function of it. And similarly, like the enable bits and so on are straightforward. The challenge is that you want to be able to route signals between the cells and between the inputs and outputs of different cells. And so there's a regular structure of what they call spans that are going both vertically and horizontally across the chip. And these are meant to let you do larger hops within the chip so that you can get from one cell to a cell that's farther away. And there are both what are called span 4s that go 4 cells over, and span 12s that go 12 cells over, and they go both vertically, horizontally. And then there's also this, you'll notice that there's this on the left-hand side here, there's a bunch of wires connecting from the left and then wrapping around to the right, that let you uh, also see the vertical interconnects from your neighbor to the right. So And each of the both the span fours and the span 12s have 24 wires that are going for each of them. For the span fours, you're sort of sliding. You're sort of sliding 12 bits at a time. Sorry, I said 20, 30, sorry, 48 wires across. And you're sliding 12 of them at a go, shifting up by 8. And the same thing happens vertically. And then for the span 12s, you're shifting by just 2 bits. The other goofy thing is that there's these crossovers where as you go between cells, on the span fours, neighboring wires cross over, and then they, get crossed over again in the next step. And at each point along their journey, for these spans, there's different opportunities to sort of hook into them. Um, so the configuration bits for the logic cells look like this. This is an output for one of the open source tools. They're 54 bits across by 16 tall, and there's some special things around the edges for carries that wrap in and out. But basically, the high level structure here is that the each 2 rows corresponds to one of the LUT units, and it's the flip-flop, and then some routing that is related to it. We'll talk. Actually, this is the first of many slides in this. So early days, I spent a bunch of time looking at the config and imagine going through this database full of numbers and trying to understand how it maps to the layout here and sort of drawing the shape of things. For these red ones on the right are the logic table. The darker red is the enables and so on. And then there's a series of layers of routing where there's groups of 5 bits that control which signal gets selected, or even if a signal gets selected. And then on the right-hand side, there's a bunch of choices for the output bits to hook them into the various spans. Uh, and to give you a sense, like this is the format of the database file. It describes for a given network number a bunch of alternate names that number has in different cells, and a bunch of routing options based on the value of a configuration bit for that thing. So lots of detail, but kind of hides the structure of things. And there's both buffers and routing, which the routing there in their terminology, routing is like an unconditional branch, whereas a buffer has an enable bit and I think has some amplification to it or something. So anyways, I struggled with doing this by hand a little bit until I resorted to Python, sadly, because it ended up being easier to build visualizations. My first attempt was to visualize this with GraphViz, thinking, oh, if I can just see, the structure of one cell, this will be straightforward. This did not work so well. This is just, if you can imagine, just one cell visualized as a graph. Not a pretty sight and very hard to make any sense of. But my second attempt was to lay out a visualization where I label the purposes of the bits, where I could both see, where each of the bits, sort of what it's controlling, and then see the lookup tables for what the different options are in line. Originally, I had in mind to print this out on a giant poster or something so that I could really pour over the thing. But it ended up being something where once I had it in this form, I could pan around. Zooming in a little bit, as you can see in this zoomed out view, though, each of the neighboring 2 rows and the bits are not uniformly sized. They're sized to fit in whatever information annotates the bits. And so each group of two rows here is a single set of LUT. It's routing for it, and then its outputs and so on. So zooming in to give you a sense, like here's these little L-shaped connections where within them there's a series of bits. One of the bits is an enable. The enable is actually obscured a little bit in the format because if you examine the format, you'll find that one particular bit, whenever anything is enabled, is always one, and so you can indirectly infer that that's the enable, and then the other ones are choosing a selection. Um, there's a little bit of a pattern to how these signals are routed. If you um, so this is showing the connection from the the spans, these SP4 values, and the neighboring outputs in the chip to what is called a local group. So there's the way I have a slide on this later, but basically there's a sort of a layering where you go in from the spans and neighbors to a local group, and then from the local group into the inputs, and then from there to the outputs, and so on. And the ordering isn't obvious in a lot of cases. That because of the positions, if you pick the right ordering for these bits, you'll get a much more consistent ordering between neighboring cells. And so there's a lot of regular structure here where if you order them in a consistent way, you'll find that you'll get an option for a particular span, and you'll notice how here you got for this position, a vertical bit or vertical span with going to span number 32, and then this neighboring one is 33, and then if you go over here, oh no, sorry, and then this neighbor is 34 on this side. So like there's sort of a good bit of regular structure. Here's the logic bits. You get your lookup table with 16 bits, and then the enables and so on. And then on the right-hand side here, there's the option to output into the different spans. And there, I actually have no idea what happens if you, on the actual device, if you have multiple things drive the same span. I imagine that would do bad things. So care has to be taken, but there's quite a lot of options for each row to route them in. And then I don't know if I have a picture of this actually. On the far left, there's also some options to interconnect between the spans, so that if you've got like a vertical, span 4 going, and there's a horizontal span 12, there are some opportunities to take the signal from one and feed it into the other. Um, and yeah, so here's an example of the routing from the input of input 0 and input 1 of a particular bits lookup table from the local groups. And the general pattern, actually, we'll talk about that in a second, but you generally have the option to input from several different local groups, but not all of them. So unfortunately, like there isn't always the option to take every possible path. There's typically a subset of them, and that's a key thing you have to cope with in the format, and similar here. So so again, as we said before, the structure is these four input LUTs and an optional flip-flop, and then optional carry as well. One of the bits can be switched in. And then the way I think of the routing is basically you've got a bunch of outputs outputs from the neighbors going up, bottom, top, bottom, left, left, and those are done in a set. And then there's a separate the upper half of each cell handles these options, and then the bottom half handles, or sorry, the other way around. The top half handles these options, and then there's options to route into the horizontal and vertical span fours. Typically, and then it's sort of not an exhaustive set for each. You then route into the local groups. There are 32 local groups, and out of those, you typically have the option for any given input to route one of 16. So roughly exactly half of the local groups are available per input. One thing that this causes that is awkward and I haven't coped with yet is that one way that you can make routing choices is that you could because you define the full lookup table for each position, um, an additional option you have for routing is to scramble the order of the inputs because you fully define how the lookup table works. So you could swap input one and three, and then if that opened up to you the possibility of a different local group being available, that would be a useful choice. So there's a lot of kind of combinations that have to be explored. And then once you do the lookup table, do the optional flip-flop, the output of that you get to write it into a horizontal span, one or more horizontal or vertical spans. So, um, challenge, right? How to do this. And I think that after looking at sort of more crude strategies, ultimately I realized that I would need to cope with this problem of being able to consider the many different paths, choosing which of the paths to go. So I wanted to model this as a graph with a node for each wire. So that's 26, horizontal cells by 32 vertical cells by eight LUTs per cell times four inputs. That's quite a lot to route. A lot of objects, and there's only 264K of main memory on this device. So representing that each one of those as an individual object is going to quickly run into memory limits of the system. So on the one hand, could this be done with an object-oriented approach? Maybe, and let's talk about how. So I'm not. I generally think that object-oriented approaches are overused. They were kind of a fad for a while, and it suffused into approaches. I think that, I do agree with the classic Alan Perla statement that it's better to have 100 functions operate on one data structure than 10 functions operating on 10 data structures. And typically where this goes wrong is you end up with sort of conflating abstraction with plumbing. And abstractions leak, and there can be all kinds of problems. But there's one area where I think that object-oriented approaches works really well, and it's actually, I think, also why it kind of took off at the moment that it did in the 80s. It's because as folks were contending with user interfaces, which are kind of like a simulation, object-oriented programming works really well if you want to do a simulation where you have a bunch of entities that all have particular behaviors, and you want to apply common interfaces to them so that you loop through a bunch of things that are kind of the same but kind of different and kind of have internal structure. And that's sort of what we have here. So there is a pattern called the flyweight design pattern. And design patterns, for those who have encountered this term, is a term in the object-oriented community for a pattern that's a little more high level than a data structure, but is reusable across different things. And apologies. I'm gonna quickly grab a sip of water. One second. Sorry about that. So the so-called Gang of Four in their famous book Elements of Object-Oriented Software Design proposed a bunch of different design patterns that are supposed to be a template for how to solve patterns. And one of them is called the flyweight pattern, which is imagine that you have a problem that you want to solve in an object-oriented way, but you can't actually afford enough memory to be able to have objects for everything. The idea is that you can separate what they call the intrinsic state from the extrinsic state. So what they mean by this is intrinsic state is sort of state that is the same across lots of elements that you can perhaps represent in an immutable way. And then extrinsic state might be things like where that object falls in context. So like its position inside of some structured situation. And the sort of canonical example is Imagine that you want to implement a text editor and you want to be extremely object oriented about it, and you want to represent every single character as an object. Particularly back in the 80s, that would have been, astoundingly wasteful. Um, so the idea is that you would have an immutable object that is the same for all of the letter A's, and then reuse that same object, that immutable object with different extrinsic state to provide it the knowledge of where it falls, and that would bring that into the realm of the feasible. Um, so this is sort of the problem here, but not quite. The You could sort of say that the type of wire, like an input, or maybe its position with the type of wire or its position within a cell is sort of intrinsic state, and then maybe the position within the overall chip is its extrinsic state. Um, but where this gave me some pause is that, to be honest, like this pattern, I've never used it in real software, and it's one of these, patterns that comes up when somebody's trying to squeeze object-oriented programs in places that don't fit very well. And it's also something where you have to do a lot of work to kind of pass around the extrinsic state. Typically this is passed around as like a context parameter to every time you invoke a method. To get with the text editor example, every single time you're doing an operation on a character, you're having to pass in the context object that represents where you're at in things. And as I was thinking about this problem, I came across a couple of observations. One is that in this particular problem, the extrinsic state is very small. While it's a big deal to have a different object for this many different combinations, that is not actually a lot of information. The number of options here is fairly bounded. And the other observation is that a lot of ultimately, especially if I'm going to do this on device, I will have to well, maybe you probably would need to build up the configuration RAM bitmap, and so you're already going to blow a bunch of memory to store that bitmap. In fact, it's something like 80 kilobytes to store that configuration bitmap. So if you've already and that bitmap represents sort of all there is to know about the configuration state. So the idea that I hit upon was, well, what if we keep the mutable state in the CRAM bitmap? And then all of the state except for the route, uh, it's small. So what if we could keep, why keep the whole object on the heap, right? The problem with representing things as objects is that if you've got a bunch of fields, you store them somewhere in the heap, and then you pass around pointers to this, you've wasted a lot of space. So the thought was, well, keep everything just as a value on the stack. And so the idea is store the intrinsic state packed in a single machine word, and then store the extrinsic state in a global structure in that CRAM bitmap. And then this has one small wrinkle, which is, if these were data types that were fixed data types where you have only, the known data type, you can do this in a conventional language like C++, where you would just represent this as a structure where you're passing around a few bit fields. But in languages like C++, when you do dynamic dispatch, you have to do them through a pointer. You can't, or through a reference. You can't have the object in your hand on the stack and then do dynamic things with it, because you ultimately have to hold a reference to it. And so the thought was, well, you need to be able to store these things on the stack, but represent them in a way that you can do dynamic dispatch. And so, a normal, just refresher, right? A normal object-oriented system, or sort of a C++ style one anyways, or a Java style one, you typically pass around an object pointer that points to some object that lives in the heap, or maybe in the stack if it's been done as an optimization. And then it has the data fields, things like, coordinates and whatever. And then there's a what's called a virtual table pointer to what's called a virtual table. And that virtual table includes the addresses of all of the operations that you can dispatch to. And so you use this to be able to handle the possibility that you might have an input wire or a local wire or one of these span wires and so on, and then have different behavior depending on which of them just by changing this virtual pointer. So you share these vtables across there's one of them per data type, but within a family of related interfaces, you can have different ones in the objects. You have to waste a whole not only put up a bunch of data on the heap, you have to um, you have to have a pointer. You waste a whole cell on referencing the vtable. So my thought was, well, let's just store this in one value. Let's figure out how much space we need to store the type, and then store the field, the X position, the Y position, the bit. And this will vary depending on the type. And then have a dispatch table that has a position for every combination of class and method, so that you'll have, a different print method for each class, a different neighbors method, a different draw method, and so on. And they're just in a 2D table. And then you can use this type field to look up which of these you want to dispatch to. And there's two different ways you could represent this, right? One is if you know the ranges of maybe there's 10 types and you've got like an X value that goes from, -10 to 10 and a Y value, then there's only a limited number of possibilities. So the most dense way you could represent this is to store them as the type plus 10 times the type plus 10 times 21 times each of the values. So you densely pack and have one unique value for each of them. That requires a bunch of multiplies and mods if you want to pull out the different values. If you want to be a little more frugal in terms of the operations, you could round up to the nearest bit. So, for 10 values, you'll need 4 bits, and, five for 21 values, 5 bits, and so on. So you could also represent this with separate bits, but ultimately you're going to pack all of these into a 32-bit word, because on the chip you're ultimately going to have 32-bit words. My desktop I have 64-bit. So I was actually able to build basically one block or roughly one block implementation of an object-oriented framework that accomplishes this. And I have two versions of it. This one is doing this first method where you're doing the mods, and the second one does the same thing but uses bits. So it's slightly less space efficient, but more maybe compute efficient. And then the way you use it, I'm not in this talk going to dig into the details of the implementation, but the way that you're going to use it is that you need to declare up front, before you do anything else, each of the different classes that you're going to use. So you'll have, for the problem space that I'm working on, I can even use this to represent each bit, right? So I can have an object for every bit. So every bit in the configuration, maybe I'll have a class that represents that. I'll have a class that represents cells. And then this framework supports inheritance, because that table you could, as you're defining elements in it, I have a word called extension that copies the dispatch table from one type into another, and that allows you to inherit behaviors. And so you could have maybe an output wire that inherits fields from the CRAM cell and behaviors, and then the input maybe is based on the output because there's 4 inputs for every output, and you could use it that way. There's some specialization for routing that I end up needing that's different per input type, and then something similar happens with the local groups. And then the span wires can also have some common behavior as well as behavior specific to if they're a span 4 that's horizontal versus vertical. And then I'll have one for not connected. And then similarly, you need to pre-declare all of the methods. And conceptually, they can fit together into interfaces that are shared. But because this is kind of a flat hierarchy, like you don't actually have to have a relationship between them. You can kind of use duck typing. So So you declare all the different methods. What I consider sort of the common interface across the cells is having a way to create one of them. And I just in general use the convention that dot create is the way that you construct one of these. And what it will do is takes the just the type parameter on the stack uh, as well as a bunch of uh, type specific inputs and then populates the fields accordingly. And then we'll talk about this more in a second, but the sort of bread and butter of all this is that you want to be able to know what your routing options are. So you want to be able to, given an object, find out how many options do I have for routing. Um, for the ith option, what other object do they route to? And then it have I selected one of the options, and if so, which one have I selected? And then a way to select one of the options, and then ultimately a way to print each of them. And this is the sort of the big slide. This ends up being my entire routing algorithm. So what I'm able to do is take a source wire and a destination wire, and then return a Boolean for if I have successfully routed from the source to the destination. And this algorithm lets me do that in a very generic way that applies across all of the different quirks of the different input types and output types and local groups and spans and all of that. And so what I do is it's a fairly simple process. I check to see if the source and destination are if I'm already routed, meaning I've gotten there. If the source matches the destination, then I'll return true. I'm done and I exit. Otherwise, I get out my current option and place it in a Forth local p variable p. And if p is non-zero, because I use the convention that zero is the default, so if I have a non-default value, it happens to be the case, and this is just a property of the ICE40 that um, when you when everything is set to zeros, it means that nothing is routed anywhere. And so a non-zero value is an indication that something got routed. And so if there's a non-zero route value here, then that means that I've already used that route for something. So that means that there's one less option. I can, if say I've routed into a local wire, if that wire is already routed somewhere else, my only option is to share that source for it. So in the case where there's an option already chosen, I go ahead and I try to route from the source to that new option, and then sorry, to the new option. So I go and pull out where does that wire route in the case where P is the selection, and then I recursively try to finish out the route. And if that succeeds down this branch, fine. Otherwise, this branch is a failure and will return false. And then if I haven't chosen anything, then I have all the options available to me. So I can then find out how many options are there. And then for each of the options, I loop through and check to see, well, if I set my route to be down that path, and then I go and explore and say, well, what if I now recurse down that branch? Am I able to successfully route down that path? And if so, then I'm done for this sub step and return. Otherwise, I undo that routing that I just did and then continue in the loop. And if I get all the way to the end and I haven't found anything, then I give up with a zero. So this recursive algorithm will combinatorically explore all of the different routing choices for connecting the source to the destination recursively. And all that's required is that I have to have a way to pass in objects that understand how to implement these get option, get wire, and so on for the different types. And there's some additional things that I use internal to the different types, things like knowing if this particular cell is a logic element, or because you can't do logic gates on top of RAM cells, or for some of the knowing which bit is the enable bit. I have for a bunch of them some common patterns in terms of the paths, and for some of them there's some challenges when you're talking about the paths from a span to an output bit. You actually have to look at multiple different outputs, And so that ends up having some complexity. So the way this framework works is that once you've declared all your methods and all of your classes, you call a word initiate, and that builds the dispatch table. And then you actually go and implement all of the different types. And so here's the implementation for one CRAM bit. You say CRAM bit implementation, and then you can declare each of the fields. And what you do is you state the bottom, the lowest allowed value, and then you state the highest allowed value. In this case, you can go from 0 all the way through the width of one. Remember there are two banks horizontally, so two banks and then -1 because you go up to 1 minus the maximum, and then that will be stored in a field, and then the same thing with the y coordinate. And so then when you go to create one of these elements, you get in an object on the stack, and then have this word put that will take in an object and alter that object so that it has put a value from the stack into that particular cell. So I will populate the y value, the x value, and then you'll notice the methods all have this m colon and m semicolon m, and they're written into that dispatch table. And so you're able to define what it means to print one of these, what it means to set a bit, which in this case calls out to yet another word that defines the CRAM. And to give you some idea with the input words, here's the definition for a zero input. And the zero input is based on a bunch of shared plumbing for inputs in general. So it's an input extension. And I have a separate way to print them because I want to print, with this label. And then I need to know where the enable bit is. And it happens that there's particular coordinates inside of that big grid for input 0. And then I have this word list bits that's shared across the different words that you'll remember we saw those patterns of 5-bit L shapes. This enable bit is one of the enable bits for this input, and then here are the 4 bits for each of the other positions. And then what I'm doing is actually taking in an execution token and then executing across each of these as a way to have an opportunity to have several words that get to loop through each of the different bits to do things like set them or get them or things like that. And then there's some, again, this is just to give the flavor. There's some goofiness around the patterns about for different inputs, you can end up having slightly different routes through them. And so there's some constants that define all of this. So anyways, the status of this tool is that I've implemented objects for all the major span types, for the inputs, the outputs, the local groups, the spans. I can route input in a synthesis language, similar to the one I showed last time with a simulator. It routes greedily, and the outputs that I generate, I haven't actually run any of the synthesized stuff on the chip. You'll see why in a second. I'm able to load them inside of the open source visualizer, so I know that they're valid because they produce a data file that you can see gates on. But there's some things that don't work. One issue is that this greedy approach to picking a route can fail fairly easily. And one reason for that is that while I can backtrack as I'm routing any given pair of wires, I don't, for example, backtrack if I I had a lookup table and I could have permuted the bits. I don't backtrack to explore that possibility. So there's issues there. Um, Also, I'll in a second look at some examples of synthesis that was done by the open source Verilog tools. The routes can be pretty ugly, and I think one of the other options that gets taken into account for those tools is they will give up and like waste most of a whole cell with a single element, and they'll do weird things like they'll use the fifth position in the cell for something and then leave everything else empty. So I think that one way out of this problem is to explore more pathways, but a different way out is to be a little bit more wasteful in terms of how to use the fabric. Um, but I can definitely explore a little bit more backtracking. Um, One of the reasons I haven't put this on an actual chip is I still haven't implemented the I/O pins or any of the BRAMs or other types like that. So I don't have a clean way to hook it up to the outside world. It's not a huge thing to do. I probably will be the thing I try next as it works enough of the time that that's viable. I don't support globals. That could be a little bit of a problem because for the flip-flops, although I support setting them up, I don't support currently routing in their enable bits, and they have some constraints on the pathways that tend to favor doing things like using global clocks. So one issue with the flip-flops is to be able to use them correctly. I probably will need to get the globals sorted out. So probably my next step would be to uh, implement just gate logic without flip-flops, connect that to some pins, and then verify that works on an actual device. In the process of making this change, I've lost my ability to simulate. I have a separate simulator that uses the same synthesis language, but in principle, there's nothing preventing me from now going back and using these Superfly objects to do simulation using the CRAM bits, and I probably will want to do that at some point. And then the other thing is I'm not calling the method that you would call on the actual device to write to the FPGA. I have it almost set up to do that, but I right now also have it writing out to a data file because I'm outputting it to external tools to verify it. So this is what the synthesis language looks like, and this is an example of me being very controlling about where the placement happens. So I have this word to locus that lets me set which cell I'm going to try to synthesize into. And this is just there's a vocabulary I need to pull in and to do things. And then so I pick up to start it at cell 10, X 10, 1. And then in general, what will happen is that as it synthesizes, it will synthesize just going up vertically and then wrap around. So here I'm declaring a 4-bit register, and then I put that into a constant. In a different position, I declare a different 4-bit register, put it in a different constant, and then I feed each of those to an inverter, and I'm storing them in a different constant. I think in actual practice, if the synthesis were more robust, you could imagine just doing this all in one expression, but I've split them up so that I have an opportunity to force it to synthesize into a particular cell. And then I take each of these two inverted 4-bit registers and I feed them into both an XOR and into an AND gate. And then I uh, switch to a storage vocabulary and synthesize this out. And here's the output in the visualizer, and it's not so pretty, but it's partially because I've in this example forced it to use some of the spans. So you'll see here's one of the two 4-bit registers, here's the other one, and it used a part of a span 12 to connect to this inverter. And then the output of that inverter got fed into both these A plus B is XOR, and then also into this AND set of AND bits. And then this bottom one used a vertical span in a similar way, and with some fairly ugly routing, uh, got into the inverter, out, and then fed into each of these. So this is a kind of an example of some ugly routing. Here it is zoomed in a little bit to see more closely. In the tool, which I'll maybe pop up in a second, you can float over one wire and look at how it routes. It's a pretty small program, right? All of this ends up fitting into 786 lines of code. There's some code for doing allocation of use of the cells, a little config file, everything you would need to sort of redefine things to use something other than the 50K variant of the chip is in this file. And then there are some separate files for layout and synthesis, which we'll look at. So what's next? Maybe allow for tracking, certainly do the IO pins. Um, I do need to do a little bit more validation of routes. Until I got the synthesis tool up and running, it was easy to think that I got the routes right. And then, as you can imagine, when I first got some of these visualizations, I got some routes that were wildly wrong, where it would sort of route off to strange stuff. Um, so now I'm going to pop out and do a demo. Let me actually go ahead and share my screen here. So to give you some sense, the all of the all of the synthesis language lives here, which is very analogous um, to the simulator that we had before. But the layout logic, which has those class declarations and the methods, uh, lives here, and it's a little hairy. And this took a lot of kind of poring through my visualization and figuring out the bit positions and figuring out the relationship between, there's a bunch of kind of arbitrary tables in here. But it's the cool thing is that it's the same for every logic cell in the grid. So as complex as this is, it is ultimately, you have the same cell essentially repeated over and over again. There's some giant case statements in here. So it's, a little hairy, but it's only 400 lines hairy. And that covers, I would say, 90% of the routing pathways, which is not too bad. There's a little bit of stuff, actually, well, maybe more like 80%. There's a little bit of routes that I haven't handled for the pathways from there are options to route between spans, between like a horizontal span connecting to a vertical span. And I left those out just because once you add those in, then you actually have the possibility of recursing back over your own tail. And I didn't want to, deal with the sort of speed explosion around it. Um, the what else can I show here? The configuration. These parameters define the layout for this particular chip in terms of the number of bit positions and things like that. And then there's some code in here for writing into that giant bitmap. Um, so let me go ahead and I'm going to build, and actually let me, so I have a different, in that slide deck, I showed a more complicated synthesis. Let me show one that looks nicer. So here I've picked some positions. I've got two 16-bit registers, and then I invert them, and then I feed them into an XOR gate. And here I've placed them in such a way that the routing is able to use mostly local neighbors, and that makes the routing nicer. So one kind of more Forthy way to cope with the problem of the routing getting ugly or blowing up is be thoughtful about where you place each gate. So let me build that to give you some sense. So as it's running, it's printing out each of the successful routes that it's discovered. And interestingly, like this is very fast if you leave out the spans. If you include the spans, it can be very slow. And then let me actually, I'm going to share my whole screen. And so over here, I've got the output. So after it runs, I currently pop up a bitmap. And so this is just the raw bitmap of the configuration. And if I let me zoom in here, you'll see down in this area, it has jammed a bunch of little bits in the different positions. And I just realized I ran, so that's the one, sorry, I ran the one I showed a different one than I meant to. Well, so that one is the config to go with the one that I showed in the slides where there was kind of that crazy routing. Let me run. This is that different one that's using the local neighbor. So instead of forcefully placing this register here and this register down here and then making them make these big jumps, I'm placing them in a way that helps the routing and makes it cleaner. So let's run that for a second. And so that output this other one, and you'll notice now here the bit patterns are all nicely nestled together, and you can see, here's one 16-bit register, another, And so let's now load that in the visualizer. So if I go load this up in if I load this up in this layout viewer, which they've helpfully put online, I can, and you have to wait for it to load an existing config. So I'm going to load this this config. So this is the same thing that we saw in the bitmap, but now in this visualizer. And as we zoom in here, you get to see now what happened is you have, in this cell, 8 bits of register bits and another 8 bits, and they all go together into a set of inverters, and then there's the beautiful routes into the XOR gate, and the same thing down here, and they cross over. And if we zoom in just a little more, you'll notice that they don't, it has to take into account goofy things like depending on what bit position you're in, it's easier to go into it had to find a pathway into the first bit or the second bit. So that's kind of constraining it in a very particular way. Ooh, I need to be careful how I zoom on this computer. So and that's in contrast to when I tried the other one, this is where I did a layout that was forced to be more synthetic, uh, where I placed the things far apart, and then it had to make use of these span pathways, which are kind of messier. And one of the reasons I did 4 bits here is that even in this configuration, when I tried to do 8 bits, it was not able to successfully find a greedy route between them, because probably what you would do if you were having things with that many bits, you would be smarter about permuting the positions of the different cells. But this one is neat in that it shows sort of these outputs. And to give you some idea, actually, let's actually flip to one of the samples. So like there's some this is a synthesis example generated by the regular tools, and these are by no means pretty routes. Like, this is doing wild stuff like placing some of the LUTs, using these 4 LUTs that are shifted up by 1, probably to get a particular position. There's a lot of duplication of the pins, mixing of some bits with flip-flops, some not. So it's a very irregular structure in terms of these tools. And so one other way I could make the Forth tool more robust is to just let it, give up and say, you know what, I can't put this, I can't fit all of the bits for this register in this or this XOR gate or whatever in this cell and spill over into a neighbor, because here, a lot of this is not
Brad,
perfectly packed.
can you zoom that window?
Can I zoom this in or out?
I just maximize the window if that's
Let me
okay.
here, let me but better yet, let me share that one specifically, because it does weird things when I maximize it, this tool. Is that clearer?
That's great.
Yeah. So you see how it's super hairy in these kinds of synthesis, and it's just because they're using in these Verilog tools a more brute force way of exploring the space of possibilities. It is a better use of the fabric. Like, don't get me wrong, like that's the right approach to fully utilize the fabric. But for my purpose, in some sense, right, what I'm imagining is the fun use case is dynamically plop down some gates, and so I don't necessarily need them to be using the system as efficiently. And so, since it sounds like it wasn't visible before, let me show the pretty one where you get these nice cascade patterns. Um, cool. And with that, I think that is it. Are there any questions?
Great, Brad. I do have a question. So you're noticing some patterns that are nice and orderly and pretty as you explain them or describe them, and then other patterns that are ugly. And I think that's a really great learning exercise for anyone who would be doing this for a living. You know what I'm saying? And
Mhm.
so, uh, you have any more thoughts along those lines?
I mean, I guess I think there is something to be said for, one thing that's become apparent to me, looking at these formats in detail, is that the designer of this FPGA almost certainly was trying to find a nice balance between being able to offer lots of flexibility for routing. They wanted, the whole point of an FPGA is to find a pattern that gives you enough flexibility in the configuration that you can map logic gates to it, but be reasonably efficient in doing it. And so it's interesting, having dug into the format to the point to be able to generate it, you can see a lot of the intentionality in terms of, they have clearly positioned things in the configuration in a way that I'm sure helps them place them nicely to be next to the lookup tables and things like that. And I think that there's very much a sense that they were almost certainly trying to pick nice numbers in terms of being able to use most LUTs and things like that. Um, so it's interesting that then the conventional way of then synthesizing to these things involves just throw a bunch of compute at trying to map it and see what you get. And it's interesting to see that doing things by hand you can I don't propose that you can do a better job, but you can certainly produce a result that is more coherent. And I think that's kind of interesting that clearly the designer of the thing hoped that you would be able to use these things in a methodical way. The spans are set up so that there's clearly this sense that they're trying to let you have a bus be able to route and fit 8 bits on that bus as it goes across the chip a certain distance. And it doesn't always quite work because they don't quite cover all the possible options of where you have to get the outputs into that bus. But there's clearly this aspiration to have a human level structure. And it's because ultimately, even though they knew they were going to throw this at a synthesis tool, they were a human designed each, the template for all the cells, and the cells are all the same. So there's this kind of interesting contrast of order and disorder in that. Any other questions?
It almost seems like a jigsaw puzzle, doesn't it? Where you could just take a piece and just try and plug them all into each other or something.
Yeah, it does. There's definitely something I kind of wondered seeing it is there a more, ever so slightly more constrained way of applying the sort of rope that you got here, such that you would sort of definitively know that you are going to be able to succeed with a route. Like I think before I resorted to this approach with the Superfly thing, that's kind of what I was hoping to find was it's tantalizing. It's for each input, you can choose 16 out of 32 of the local wires. Like one more bit, and they'd have been able to route into all of the different options, but they chose one bit less, and that's probably because the cost is not just the config bits themselves; it's all of the semiconductor space to be able to implement those options. So it's this weird trade-off of, oh, you almost gave a full, sort of the full range of possibilities, but not quite. Is there some subset of the architecture that gives you full connectivity, and then you could sort of confidently know that you could always route things like that?
It was kind of reminding me of the biology stuff where you got letter combinations for DNA, and you've got these things of this thing about like locks, and the things fit together like a puzzle in biology. Or at least this is a model in biology, and it's like maybe we could have the same model in electronics where things fit in a certain way.
Yeah.
Except of course in biology the fabric's set up a different way. So, but still, the concept that you use in biology might be useful in electronics if you can fit pieces together, just like you can in biology, I guess. And we've got algorithms to do this in biology. So if you got the algorithms from biology, maybe you can use them in the computer stuff as well.
Any other questions?
Uh, I have definitely some commentary, and maybe since unless there's some intervening scheduling, maybe just sort of transition the time accounting.
We're good in that regard. If you want to
Yeah, because I
focus on
mean,
that, the only person's time you're taking is really your own. I don't think anybody is desperate to do the challenge, and there's the two items left on the agenda today.
yeah, well, and actually, most of my notes are about the challenge. Let me
Cool.
Hold
share.
on just one second. Um, Brad, that was an awesome talk. I can tell you're doing a lot of work, and I really want to just thank you so much because I'm highly interested in what you're doing, and I think it's really going to make a I'm trying to actually on my end of it, I'm trying to do some fourth. I'm trying to develop like J1 soft core uh, like different kinds of like variations of that and so I'm so interested in what you're doing because I think it's going to dovetail somehow with what I'm doing. I don't know how. Anyway, I just wanted to say thank you so much, Brad, and what a great job. All
Thanks.
right,
Thanks.
thanks,
It's a
Bob.
fun jigsaw puzzle, as Paul said it. Yeah, so yeah. Although I have to say I'm kind of glad to finally see some of the routes lay out. I was getting pretty sick of the staring at the bits. So